All right, I think I'm just going to get started on pull requests here. There's not a whole lot to go over yet, but let's see. Peter, you've got a new one here that I think you maybe entered in. Do you want to talk about it at all?
Actually, there is not much to say here because this is long-standing idea I had, and finally I had some time to research this properly, and it looks like if we just combine log rise into fewer syscalls, we might have better performance in high log situations. So it's pretty obvious when you think about it.
It sounds good. Yeah, I think we have maybe some long-term ideas about getting away from our current logging scheme in general, but anything that we can do to ease the pain is good.
Yeah, this should be fairly easy to backport to Luminous, for example, so others can benefit from this. And I
Cool.
know I have first-hand performance experience of how production works on debug file store on high level, so
Yeah, that would help a lot, and it's even worse with BlueStore debugging. So
yeah, I actually researched this on.
Cool. All right. Well, the other new PR we've got here is Igor's, and he has a whole presentation about it. So we'll move on. We'll discuss that once in a little bit here, I guess. For closed PRs, there wasn't also a whole lot going on. I think Kifu closed both of these here that merged. Yeah, I didn't really look too carefully at these, to be honest. I think neither of them are real big. And then there was another one that got closed, which I'm not entirely sure why, but I assume it must be related to all the RGW rework that's going on. Maybe this was no longer necessary or no longer made sense. And yeah, that's about it. The only other thing I guess I'll mention is there's this PR by Adam that Sage was able to review, and it's a little tricky because it involves kind of changing some different things that are a little scary. So I guess the thought right now is maybe to do a little bit more investigation on it and figure out kind of if it makes sense or not. So I think Adam and the user who is testing this are going to try to investigate a little bit more. Beyond that, yeah, not a whole lot going on. Well, anyway, so yeah, that's basically it for pull requests. I will have another one coming in soon, hopefully for cache balancing in BlueStore, which I think is going to be really exciting. But we'll maybe talk about that next week. So Igor, want to see if you can get your slides to share?
Yeah. Can you see my screen?
Yes.
Great. Today I'd like to discuss what I have so far with new bitmap allocator for BlueStore and present some comparison against existing stupid allocator, some interesting numbers. That's definitely not the complete research, and actually I suppose there are plenty of different scenarios when that should be covered by testing, benchmarking, and probably not that good. But let me present that what I have at the moment. The benchmark were performed using HP DL380 server that has two Intel Xeon CPUs and OpenSUSE Tumbleweed operating system. And I used Intel 750 SSD for both block device and database device. And following settings were applied when applicable. There is an open pull request that contains all the code and benchmark, at least some of them, as well as here is the link for that report. First of all, let me run through this new bitmap allocator design. So the intention is to to control the space that BlueStore uses for both user data and for BlueFS data that contain mostly RocksDB stuff. So, actually BlueStore can have multiple instances of this allocator, one for raw data, for block data, and 2 or 3 for BlueFS. But anyway, each space that allocated instance is controlling is logically split into allocation units, which are 4K or maybe 64K by default for user data, and about, if I remember, 2 megabyte for BlueFS things. So here I introduced the L0 level, which has just a single bit for each allocation unit for underlying store. And to speed up the lookup during the allocation, 2 more layers were introduced, L1 and L2. At L1 layer, each slot is equal to 2 bits, and following values are used to determine the state of the corresponding subset at L0. And at L2 layer, just 1 bit is used to control the underlying L1 slots. One thing to mention here is that each layer, this data layout was organized in a way to benefit from Intel's cache line alignment, that is 64 bytes. So you can see that well, each bit from L2 is mapped to 64 underlying bits at L1, and each 2 bits at L1 are controlling again 64 bytes at L0. So this way I'm trying to speed up the allocation. Instead of enumerating the whole L0 bitmap, it's trying to build sort of tree structure. And again, it's trying to benefit CPU caching. Any questions so far?
Yeah, are those spaces contiguous in actual physical memory, or they are separate? Like
yeah, each layer maintains a continuous memory block, at least for now. There are some thoughts about optimizing memory representation for some cases, and maybe, well, I left some things to potentially migrate to discontinued blocks. But right now, each level is in continuous memory block.
Okay.
Okay, some design considerations for this new bitmap allocator. As I said, it attempts to align data with CPU cache line. Also, it attempts to operate on 64-bit values wherever possible. And this tree-like data structure enables much faster lookup. And potentially, we can benefit from concurrent allocation request handling. Right now, stupid allocator is able to, well, while it performs the lookup, it locks the whole data structure, so it handles just one request at a given time. Actually, new bitmap allocator is also handling just one request, but potentially we can, using this design, we can handle multiple concurrent requests. For instance, by having independent logs per set of slots at L2 level. Another thing that is doubtful, probably, as it has both positive and negative impact, is a fixed memory consumption of the allocator. So, contrary to stupid allocator, we allocate all the space that is needed to maintain that tree on startup. Well, we can predict how much space our OSD in that respect will take from one side. From another side, this memory consumption can be pretty high. Here are some estimates. Well, actually, actual results of what I observed. So it's about 130 megabyte for 4 terabyte store and 4K allocation unit. But unexpectedly, I observed that stupid allocator memory consumption might be pretty high as well. So actually, that's not that huge issue, I suppose. And the last item to mention is that currently there are at least virtually two modes of allocation that we need in BlueStore. The first one that is used most often is scattered extents allocation. So we don't need the contiguous space for user data storing. And that's the thing that new bitmap allocator do the best. While contiguous allocation is required for BlueFS during rebalancing space between BlueFS and raw data. And actually, that's a rare case while comparing to regular mode or regular override operations. And actually, I haven't done some extensive benchmarking of this mode, but I can expect that in some in the worst cases, this current implementation isn't effective because it might need to enumerate the whole bitmap. Well, again, in the worst case, when the space is pretty fragmented. So all the results that are below are mostly for scattered allocations so far. Any questions so far? Okay. So here is an overview of the test cases provided. The first subset of test cases is a direct allocator usage. That is just a sort of code written based on existing unit test infrastructure that calls well, both stupid and bitmap allocators in specific way in a loop without any multi-threading, multiple concurrent access, etc. So the simplest case is just a sequential 4K block allocations followed by the sequential release. Trying to allocate the whole space that is 1 terabyte for this set of cases, and 4K is for allocation units. The second, that is mix full, is a bit more advanced test case that allocates blocks from ranging from 4K to 2 megabyte of size, selecting randomly the sizes randomly, mixed with randomly selected free requests that are shorter. So the range of sizes is shorter. It's just up to half a meg. And this allows us to, so actually the memory consumption is growing, and the test case completes on the whole space when we cover all the space. The third test case is to allocate 50% of the space sequentially, and then do a mixture of random allocations and frees of the same size ranges. And well, actually that doesn't take all this control space because we have balanced allocations and releases. But the total amount of data that it performs allocation for is currently 3 terabyte. And the fourth and fifth test cases are similar to the previous one, with just 90% of space pre-allocated and 10% of space pre-allocated. That was the direct allocator usage. The second subset is benchmark based on Object Store FIO plugin. So we have BlueStore here involved, but we don't have the actual cluster, OSD code, network, etc. So this test case performs random overrides over pre-filled storage for half an hour. The total amount of space taken by the objects is 48 gigabyte. And there are two options. The first one is overwriting using 4K blocks always, and the second one when block sizes vary from 4K to 128K. Any questions? Okay. And now the resulting numbers for direct allocator usage. And one can see that actually bitmap allocator wins in all the test cases, and some numbers are totally different and much better. That's pretty unexpected, at least this huge difference for me. That's pretty unexpected, but that's what I have so far. And the second slide is the the same set of test cases, but it covers memory consumption. So you can see that for bitmap allocator, memory consumption is fixed, and it's higher for sequential cases, the first two of them, when stupid allocator is much better. But eventually, for the last three test cases, memory consumption of stupid allocator grow significantly, and that's pretty unexpected for me. At least these large numbers, and maybe it makes sense to analyze that why it behaves this way one day.
Igor, on the memory usage in the first two cases, is that because the tree is just really small in the bitmap case, or in the stupid allocator case?
Yeah, I think so, because due to sequential sequential scenario, we just cut a part of from the bitmap and take it away, and the actual tree is it stays the same. So it's interval set as far as I remember. So it just reduces the single interval, at least for sequential case for the first column. So stupid allocator, since it maintains just free space extents, it just needs just one interval to maintain the whole space.
Yep. Okay.
And here is here are the numbers for FIO plugin benchmark. The first column for 4K overrides, and the difference isn't very much, but probably expected. But the second column again is pretty unexpected for me. It's when we range, we vary the written block sizes from 4K to 180K, and the difference is dramatic. I don't know why. Well, I suppose the root cause is probably the same as for previous test cases, but that's strange that nobody observed that before. So maybe I'm wrong here somehow. And the fourth chart is about again mem usage. Again, stupid allocator mem usage is pretty high here, while bitmap 1 isn't that high, and that's because that's just 2.5 megabyte, and that's because the store that I was using is pretty small, and bitmap allocator hardly depends. Its memory consumption hardly depends on the actual store size. Well, any questions?
It seems like as you target really huge devices, it seems to me like the bitmap allocator should like not do as well as you end up with more and more chunks. But it seems like your testing is almost showing that the stupid allocator does worse.
Well, since I provided some estimates on the memory consumption for 4 terabyte drive for bitmap allocator, it's about 128 megabyte. well, 130 megabyte. Here we can see that stupid allocators, well, takes tens of megabytes in even smaller, much smaller stores. I'm not sure if it grows linearly with the store size. Unfortunately, I don't have the size of the stores of the disk of that sizes. But I don't think it grows that it grows linearly. I mean, stupid one, but at least the current memory consumption is comparable. So tens of megabytes.
Yeah. I'm curious with, like, really big disks, like 10 gigabyte or 10 terabyte disks, and as we go into that, if we'll end up with more memory consumption with bitmap allocation versus B-tree. But right now, I mean, your results look really good compared to stupid.
Yeah, well, I mentioned that I have some ideas on compacting the representation for this bitmap allocator. So for some fully filled slots or fully empty slots, we can probably well, compress that somehow. And I left some bookmarks in the code for that. Maybe I can return to that optimization. And well, again, another thing to mention is that 4K allocation unit for terabyte drives is pretty small. As for rotational drive, we use 64 K defaults, and this will reduce the memory consumption at 16 times, and so 16 times less from 120 megabyte isn't that large amount of RAM. But well, definitely this should be tested more elaborative. So just some initial results I have, and they look pretty interesting for me.
So these are all testing on the 400 gigabyte SSDs, right?
Sorry?
These are all tested on the 400 gigabyte SSD disks that you mentioned earlier?
Well, the first subset of test cases is just simulate 1 terabyte. So no actual writes here, just virtual space that we are splitting into chunks. And the second subset was for against pretty small stores that is about well, actually allocated space by the object is 148 gigabytes, and the stores themselves were about 80 gigabyte per block device and 70 gigabyte for database.
Okay.
But as I said, the memory consumption for bitmap allocator is completely predictable. So
right. I'm curious about the I guess the throughput differences as well. That's kind of surprising to me, I guess, how big the difference was. I'm curious if this would even be a bottleneck on hard disks at all as well, or if it's only going to affect faster devices.
Yeah, that's actually an interesting question. Yeah.
It seems to me like traditionally with hard drives, it's more how much fragmentation we end up introducing by the allocation scheme more than anything.
Yeah, and that's another aspect that probably should be tested. And in that respect, bitmap allocated might be completely different from static one. So it might be a completely different picture of the fragmentation picture layout. I mean. Well, and finally, some observations about the existing stupid allocators. So I haven't investigated that much, but just to mention. The first one looks like hint functionality stupid allocator provides at the moment might have pretty negative impact on the performance, especially when this hint wraps or even allocation. At least I saw that it drops about 3 times. Maybe that's the root cause of that huge difference. The second one already mentioned is pretty high memory usage. That probably means that it doesn't perform defragmentation well. And the final one is that current reserve plus allocate interface with 2 calls to allocate to handle allocation request. It seems redundant, and probably we can stay with just single direct allocate call. This saves an additional mutex log, and I observed about 5% of memory improvement for this FIO plugin test cases, and that's in a different pull request at the moment. No, actually, that's all what I have.
Coming to the last one, if we don't have any space reserved, let us assume, right? So how do we guarantee the allocation will go through? So right now, what it does is actually it reserves something and then it doesn't allocate, so that it is space for this write is guaranteed. Or else we should have a global reserve, maybe a 5% or 2% kind of thing.
Well, actually, we can move all that code from reserve to allocate, directly to allocate, and return from allocate immediately if you don't have enough space. Because if you look at the code, all these reserve allocates are in pairs, so then they are following each other. So there is no case when we reserve some space and postpone the allocation itself. In my opinion, there is no sense in splitting them, but you need a lock in each of them. So that's the rationale.
Yeah. The lock is redundant, yes.
So this can be performed just in a single step. That's all.
Yeah. More than that, actually, I'm thinking about if we can actually, do we need any global reserve to kind of get through some of the IOs? Let us say maybe 2%. We can just say okay for the infinite IOs.
Yeah, maybe. And one thing to mention here is that actually reserve doesn't guarantee the actual allocation because, well, especially at least in cases when we need contiguous space, we can face the case when the available space is enough, but the fragmentation prevents us from the allocation, and we actually need to handle what happened after the allocate, so it still can fail.
Yeah, true.
Well, at least for that rebalance procedure for BlueFS rebalance procedure when you need contiguous space.
Igor, I was wondering, have you thought about hybrid schemes at all that use both B-trees and bitmap?
Well, I have some thoughts about introducing maybe some caching prior to bitmap allocator one, and this caching scheme might rely on some tree structures. Yeah, but just some thoughts, and I haven't started coding in that direction yet.
So what are you planning on testing next?
Uh, well, I don't have specific testing plans at the moment. Just probably going to have some feedback on all that stuff and then decide which way to proceed.
Sure, makes sense.
If I can suggest something, that you could, for example, test the low disk space situation. How does the low,
which situation you mentioned?
low disk space?
Low disk space. Yeah, but yeah, got it. Okay, we'll think about it. Well, actually, this test cases cover that a bit because, well, at least this one is working on 90% of allocated space, and this two works on well, they fills all the space, so at the end they operate on the already on mostly allocated space, but maybe it also makes sense for that more real scenarios that with object store.
All right.
Yes,
Any other? Yeah, go ahead.
Did you measure the CPU usage during these tests? I'm wondering if the throughput difference was related to CPU differences or something else, just like fragmentation. Or...
Well, for the first subset, it's always 100% because that's performed in a loop. For FIO stuff, I haven't checked that.
Okay, yeah, that makes sense.
Maybe it makes sense, yeah, to do that. But I don't think we can see much difference here. But well, anyway, yeah, probably. So originally, my idea was that in that second subset we wouldn't see much difference because actually allocator wasn't considered as a major bottleneck for BlueStore. So even if I improve the performance considerably, it shouldn't exceed, well, maybe 1 or 2%. But well, that results that I got seems strange. So this means that in some scenarios, allocator might dramatically impact the performance. So
Yeah, and that seems pretty interesting. I'm curious why that is, if it is related to CPU or memory allocation patterns or what.
yeah, maybe that's a good direction for investigation as well.
Once we hit the fragmentation, maybe getting the bigger allocations will be a challenge if you're doing a 4 MB right kind of thing, right? So
yeah, but the interesting thing here is that for regular write operations, we don't need large contiguous allocations. So doing large scattered allocations isn't a problem for bit map allocator.
we can, but our meta can go a bit high. It will be a random. I mean, if you are talking about an RBD kind of thing, yes, a block, right? So it will be like 1024 with the worst case 4K writes. And
No, okay.
and then I mean, if I'm doing a full 4 MB write, in that case, once I do multiple 4K rand writes, which fragments this, maybe finding a 4 MB allocations might be taking more CPU on a bitmap too, right? And unless we have a zone kind of allocation, I mean, you reserve something in a bigger chunk.
Well, just some thoughts, preliminary thoughts, I'd say that currently for this new bitmap allocator, allocating
Yeah, right now this is actually a
well, I agree with high high fragmentation. The impact might be so.
right.
Yeah,
Yeah, I mean,
might be more
on a
difficult
big,
to
yeah, on a
locate.
bigger disk, yeah, on a bigger disk size, I think it is more, will be more. Once we start going beyond a couple of TB of the size, it will be more CPU time. We would be searching for the free block.
Yeah, maybe probably it makes sense to analyze it.
I think that's the reason the stupid also is doing a bit worse, because we try to kind of scavenge them in those minilog sizes and try to put it in the interval tree. So and as and when it gets fragmented, we will consume more memory there compared to the bitmap. Bitmap is optimal on the space, the memory usage, uh, but it might consume more CPU. I mean,
Yeah, got it. Okay.
One of the things that we've kind of seen in the past with stupid allocator and I think bitmap allocator even worse was that exactly what you were just talking about, Verada. After doing a bunch of small random writes, you could see an impact from fragmentation on further like large read and write tests.
yeah. So I mean, that is the worst case what we did too that time. So you do a full sequential write and then do a complete rand write on a block device, and then we do a sequential write. That would suffer a lot.
Yeah.
I mean,
So the good news though is that we've got some tests already that should be able to showcase kind of that behavior and how this compares to the stupid allocator. But yeah, especially on like hard disks that and I think even maybe a little bit on NVMe, it was we were worse in that regard than like XFS with file store.
yeah, maybe the file systems do a better allocation there, right? So because they have these regions, and then they manage these zones, allocation zones, so that they're always guaranteed to get something.
Hello?
Well, go ahead.
No, just it looks like I lost the connection. Sorry.
Oh, nope, I don't think so. But unless anyone has any more kind of last minute questions, I don't think. Well, yeah, unless Igor, do you have anything else that you wanted to add?
No, nothing from my side.
Okay. Well then, anything else, folks?
Hi, Mark. I've just got a little topic I'd like to discuss.
Sure. Go ahead, Nick.
It's our old favourite PG num, sort of purple. I've just been thinking about this recently. With sort of the recent release of 14 terabyte drives and sort of massive flash NVMe drives as well, I'm sort of just trying to understand the sort of thought behind the sort of the 1 to 200 PG per OSD, because obviously, although that works historically, with a 14 terabyte drive, you start ending up having a lot of data per PG, which is obviously going to affect recovery speed and stuff like that. But also then with NVMe disks, you're going to be having a lot of I/O going to a single PG and getting contention and so on. So how does that work going forward? Because I know there's going to be some work automating. How does that sort of work going forward in terms of either large capacity drives or large I/O drives?
It's really tricky, at least in my opinion. I mean, maybe other people have thoughts on this, but we already have a lot of work being done just given the number of PGs that we already have when we look at PG log and everything else that's going on. So figuring out how to there's so many factors that go into this, right? I mean, we have the balancing aspect of it, and that's kind of now being taken care of by some of the work that like Loic and Sage have done on PG balancing. But that doesn't get you away from kind of the other problems with contention, like you mentioned, when you have a huge amount of data relative to the number of PGs. And then, increasing the number of PGs increases the workload in other areas that I think we're already struggling with. So, from my perspective, it's a hard problem. I'm hoping that if we kind of change the way that we do PG log and dupops and PG info, that maybe it will allow us to, one, not have to keep everything in memory, which we can't, that's not going to scale. But then also maybe it will reduce the amount of work that we end up doing overall per PG, and maybe that will have some positive impact in terms of being able to handle more, or at least be able to handle the current number with less overhead. So that's my take on it. I don't know.
Okay. I mean,
Josh,
is it sort of the case at the moment that, if you say you were going to have, 14 terabyte disks, do you just need to sort of maybe spec your machines with more resource to just pretend like you had more OSDs? So if you've got, say, 10, 14 terabyte OSDs, should you just be specing your host to have, like they were going to have 26 terabyte OSDs, and just sort of give it more memory, more CPU to sort of make up for the fact? Does that make sense?
So are you asking that if you have large disks, should you be giving them more resources and then also simultaneously upping the PG count, or just leaving?
Well, are you talking about like new clusters, or just you're going to stick them in an existing cluster so they're going to get more PGs?
Either really.
So I mean, I think with new clusters, in terms of balance, it doesn't really matter that they're larger. The statistical properties don't change much. What the time to recovery for PG that you mentioned is interesting, and not something I think anyone's thought about very much. But it's just sort of a general consequence of having a larger storage device without a larger throughput. That's the storage wall concept. So yeah, I don't think anyone's running any experiments about increasing the numbers to deal with the recovery time. But leaving that aside, if with a new cluster, I would probably just stick with the standard PG recommendations. If you're going to put it in an existing one, then yeah, they're going to get more PGs, so you should probably overspec the machine. That would.
Okay. Yeah. Okay. That's cool. It's just there was two sort of different diverging things here, that the devices are getting faster, handling more I/O, and then other devices getting bigger, and that they both started hitting limits. So I was just interested to raise that as a discussion point.
I mean, there's a lot of work going on to deal with devices getting faster. Kifu's pressing ahead on C-star, and there are various people doing micro optimizations and characterizations so that we know where to focus work and things. But
yeah.
that's all I had. Anybody else? Josh, have I missed anything?
I think you guys covered it pretty well.
So yeah, we have a different problem. We have a bigger disk, but the IOPS are not high, because if we are thinking about a hard drive kind of thing, right? So the disks are getting around 14 terabytes and all, but that is not fast enough like an SSD, right? But I can hold more PGs, but it can do only 100 Mbps or maybe much lesser than that in case of a RAND IO, right? So in that case, I don't know. I mean, so what? One of the things is mostly what we do is a backfilling. We don't we have a lot of PGs though. Per OSD, I think we have around more than 200 or 250. So what we did is we actually got the windows of this PG stuff to maybe less than 1,000 there. So we mostly backfill if we fail, but we don't consume more memory there.
Yeah, the hard disk case is a bit different because you can't just throw more resources at it. The bottleneck is the hard disk itself.
Right, yeah. So, I mean, so we have a mix and match of both. We have an SSD kind of a cluster, and then we have the hard drives as well in that. I mean, a cache tier mode also is enabled. That's where we have this challenge. So, recovery goes faster on SSD levels tier, and then it is very slow on hard drives. And most of these uh, controls are kind of global to throttle them, some of them.
Yeah, I think we're talking about the same thing. Is that with the larger disk, because you've got the same amount of PGs, you're not spreading the recovery. You can't spread it. You know, if you had 1,000 disk cluster, you can't spread it. The recovery over 1,000 disks of 100 PGs roughly, you're only spreading it across 100 disks, which means the difference going from a 1 to 10 terabyte disk in I guess in the lifetime of the Ceph project has meant that you can't spread the recovery any further.
Yeah, that's true. I mean, we're mostly bottlenecked at the hard drive case, right? I mean, there are not enough IOPS to really make recovery faster at this.
But what it means, if you had the number of disks in the cluster to make recovery faster, if you had 1,000 disk cluster, you should, if you didn't have this PG limit, that wouldn't be a limitation anymore.
Well, but that just means that you're still that you're devoting an ever larger portion of your cluster's throughput to the recovery rather than serving client I/O.
Yeah.
And I mean, if that's the case, you're still like if you lose one disk, yes, one PG will take longer to recover, but you're still going to be all the OSDs are going to be doing recovery of their PGs, and it's just going to take a while because there's a lot of data, and not a lot of IOPS, but I'm not sure that the densities actually change that much.
Yeah.
Just
You effectively just increased your failure domain by having a larger hard disk. Like it's the same effect as having multiple smaller disks fail, right?
Yeah, I mean, so this isn't so much for, I guess, for throughput work. It's for a lot of this, from my angle, would be more for sort of people using sort of archiving or sort of very low demands, but still sort of are looking at Ceph as a way of sort of getting high data durability. Which is one reason, for, I guess, for using Ceph over something like RAID, where you are stuck by ever increasing rebuild times. Sort of one of the attractive things for using Ceph might be that you can get these recovery times down.
right, but I mean that's still the case, isn't it? So yes.
Dramatically so. It was just.
Well,
yeah.
but I mean, so in this case, an individual PG takes longer to recover, but you still got 100 PGs that are recovering across the cluster. It's just that you lost, 14 terabytes of data instead of 7. So yeah, it's going to take longer.
Yeah.
And like you mentioned, for the large SSD case, you could increase the memory and CPU for those boxes and increase the PG count, and you might be able to see that speed increase for recovery. Though I don't think we have tested that in particular.
For the faster like NVMe case, it wasn't so much about the recovery time. It was more around a like sort of PG contention about more and more IOs hitting a certain PG.
Mm-hmm.
Yeah.
We absolutely still see locking issues too, where we're gonna, as these things get faster and faster, we're gonna be spending more time in PG lock, I think.
Yeah. And this is where today we've in the past seen folks already running multiple OSDs on the same disk but with different partitions, right?
Yeah.
Yep.
Because what I've seen, if you've got a load of VMs that they've all got XFS journals or something running inside the VM, you tend to get a lot more hotter small areas rather than if you're doing a sort of let's just do a complete random benchmark across a block device.
That's interesting. Do you have any like results showing that kind of behavior?
No, I might be able to start collecting some if I can get some free time from some of the projects I'm working on at the moment. But yeah, I have seen stuff. Certainly, if you're doing anything that is sort of like more synchronous I/O, you definitely start seeing it build up because especially like if you're using like XFS on like an NFS server or something, every write has to update the XFS journal, which is obviously sitting on the whole thing sitting probably in a couple of RBD objects.
Sure. Mostly reads or writes too, or both?
Right. So this would have been mainly write workload.
Okay.
It's the XFS journal. It's an intent log.
You're right. Yeah, it'd be silly for it to be reads.
Yeah.
It just kind of made me wonder if the RBD fancy striping of striping would end up putting that across more objects and getting more parallelism per VM that way.
Yeah, it's something I need to look at and try. Yeah.
The RBD people would hate this, but we could start introducing variable layouts where the front of the drive gets a finer granularity because we think it's going to be a journal. Did that not make sense to anyone, or are you thinking about it? Because the two people I can see are making blank stares.
I'm trying to think about it, but it's still not making sense.
Yeah, I'm not sure how that would work.
Can you say it again?
Well, so right now we have a layout across an RBD device. It's by default it's 4 MB chunks, but you can have it stripe across them in 64K pieces across a 4 MB object or something. We can make
Okay,
it
you're talking about
100 objects are
right.
fine grained fancy striping, and the rest of it's larger.
Okay, yeah.
I'm not sure there's
You're
really
right.
a disadvantage of not doing it all fancy striping in that case if it helps, but
Because it's just a simple heuristic for matching up the kind of I/O you're going to see on which regions of the drive and how frequent
yeah,
the object accesses are. That said, I mean, it's not here yet, and it's not going to be a lot of incremental gains. It'll just appear one day, but the like the C-star work and things are designed to deal with a lot of the PG overhead and contention. So, like the locking issues. So that's our current plan for dealing with it.
yeah. Once we like that, have a move over to C-star, we eventually get rid of the PG locks and only have the per object contention, which would still affect this case of XFS journals, right?
I mean, probably not so much because mostly it has to wait for them. Like, there's only so much pipelining it'll do. But yeah.
Yeah. Well, in any case, I think that's a good point you brought up, Nick, about the XFS journals. We probably should do some more testing around that.
Okay, yeah.
Is there any possible way that we could do something, Josh, like we had kind of hypothesized earlier about having some kind of like log interface at the Rados level?
I don't think there's really anything that would help particularly well for the parallelism aspect of it. I think that that's mainly like what we've talked about before is mainly about just not using an LSM tree to store a log data, which is already the case for RBD. So I don't think it would be much of a benefit. Like you can't write less than what RBD is already writing for an XFS journal, I assume. So I don't think the layout changing would help.
If we this doesn't really help in the case where it's like lock contention and on really fast drives, but on hard drives, if we did some kind of internal caching on the SSD of really hot blocks, then you could have the XFS journals for RBD, the objects that those things are on, sit on the SSD or NVMe drive or something.
Yeah, potentially.
It's not so much. Sorry.
Oh, I was just saying there was a PR like this a while back where someone had made something that let you, I think, if I remember right, I think it let you like stick stuff on the SSD for BlueFS, like get stuff over there instead of just sticking it right on the block drive for hot things.
Mm-hmm.
Sorry, Nick, what were you going to say?
No, I said because I mean it's not just I guess so much the internals of Ceph itself that cause the problems around the contention. It's because it's obviously a distributed system. You've got network latency and all the whole pipeline of latency building in there. That if you are waiting on a PG, you've got to wait for stuff to shift around everywhere before the next client can do something. So it's not purely just probably down to making the OSD faster, although that does help a lot. There's a sort of other aspects as well that are probably outside the control of Ceph.
I think in that case we just need to go and implement that back off on all the clients as well, right? So the RBD, or if we are actually not able to serve a lot of IOs due to recovery or something, right now we have this backoff, OSD backoff thing, right? I mean, should be implemented at the client level to handle them on a PG or something which is actually takes more time to recover.
I think that's kind of a separate issue, but that's how they're implemented in, I think it's in Luminous, at least in my Mac
Yeah.
at least. But yeah, where the client is backing off and sending more apps for longer periods. Right.
Yeah, I don't know with all the RGW or RBD actually handle that backoffs right now. I don't know. I mean, I haven't
But
seen
yeah,
them right now in Luminous.
yeah, it's handled in the advocator layer, so everything about on the client side is benefits from it.
Okay. Yeah. So yeah.
Well, I think we've exhausted our time, guys. But Nick, it's interesting to hear. It's something I think for us to think about more.
Cool. Yeah.
All right. Well, thank you, Nick. And it looks like Igor's gone, but thanks to Igor as well for the good presentation. And we'll meet again next week. And have a good week, everyone.
So.
See ya.
Yeah. See you.
See you guys.